Hello, am I audible? Okay. So, yes, so this is a revision session. Tomorrow is exam, I think. So, do you have any doubt regarding anything in the course? Sorry, you cannot hear. Can you put that in chat? Okay. Okay. Uh, so tomorrow at what time do we have exam? 9 a.m. Okay, morning only. So I have actually prepared some 9 questions or 8 questions. So it's like previous year question. So it will be helpful in that sense. So we'll start the class at 7. Still not 7. If you have any doubt, you can put in the chat. Okay. Okay. I will start now. So our first question is uh, it's pretty simple because it's just differentiation in chain. So I think no doubt here. Uh, Actually, the del operator also works in the same way. So del operator, if, if this is two functions, w and v of some, uh, so w and v, if it's a functional, is there negative marking tomorrow exam? I don't know how the pattern is. So I am assuming it is same as the what assignment you have solved. So you can check on with the technical page. In page the instructions are given. Okay. So if we have two functionals, then also it will be if functional comes. So now the second question was which of the following is true about. Now we have solved lot of um, we have converted a lot of system into these matrices, and in my tutorials we actually did for this mostly. This Q is for a natural uh, boundary condition. In altogether, it is that force is equal to K into U. So the question here asks is this F, what does it represent? So it represents external force for any type of governing equation. So that is false. because it depends on this governing equation. K is dependent on the governing equation. Depends on the governing equation. Okay. So first one is false. The next is F represents the term related to external load, both point and distributed load. So this is true because this F contains everything. What happened to distributed load? That is also converted into these discrete points, and I will give example of distributed load. So let's say there is a beam and some forcing was like this, having some magnitude as uh, let's say Q Newton per meter, and there is one more concentrated load like this, and its value is F. So the finite element method, what it does is first we discretize the space. So let's say we say that instead of this whole beam, we are taking only these 5 points. All right, and let's say if total length is L, so we have put discrete point at L equal to x equal to 0, and this is x. So at x equal to 0, then x1 is at 0, then x2 is at L by 5, x3 is at 3 L by 5, x4 is 4 L by 5, and x5 is L. Okay, so we have taken 5 discrete points. So the forcing will be written as Q into, so equivalent loading I am writing in this pink color. So there will be, let's say, forcing F1, then F2, then F3, F4, and F5. Okay. So this F1 value will be Q L by 5, F2 value will be Q L by 5, F3 value will be Q L by 5 plus F, and F4 will be Q L by 5, and F5 will also be Q L by 5. So this force vector, it has distributed load, which is this, as well as the concentrated load. Okay, so hence that is true. Now next is F represent the term related to distributed load. So it's like they're asking only distributed load. So this is also false. And F represent the term related to point load only, and this is also false. So next is what is meant by weak formulation. So I have a definition of weak formulation written here. So guys, if you have any doubt, you can ask in the chat. I will try to answer it. So this is just last thing, this last minute to minute thing which we can discuss. So a weak form, what does it mean? So what we are doing, we are taking an integral of a, we're taking a differential, oh, sorry, integral of a differential equation. So in the whole course, what we have done is we have tried to formulate the weak form from the maybe energy or maybe from the strong form. So if we are taking strong form and finding the weak form, then we use weighted residual form with weighted residual methods. And if we are going for from the energies, then we get it from Hamilton principle. So this definition is given in Reddy book. Integral statement. So we will go through the options now. Solutions obtained are incorrect. No, these are uh, obviously incorrect, but we are going for approximation. So the better statement would be solution obtained are approximate. Next is the differentiability requirement on a primary variable is decreased. So this is the correct answer because the weak form it is integral of a differential equation. So in that way, the differentiability requirement it decreases. Okay, because we have given more power to the differential equation. So obviously, third one will be false. Then no boundary condition have to be satisfied. No, actually, when we are going from energy method or via Hamilton principle, boundary conditions come itself in the equation. All right. So that is one more benefit. Now, next question is, just check the chart. Okay. How exactly the theory learned in this course is useful in industry? Okay, I will keep this question for later phase because actually I wanted to just ensure that everyone do well in the exam. I think this won't be asked in the exam, but just be with me. After solving this 8 questions, we will come to this question. Okay. 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 That's okay. Okay. Moving on. So to solve the time dependent problem using FEA method, first step we need to do is element level is. Now we have two options actually. One is temporal approximation and one is spatial approximation. What does temporal approximation means is we are describing the time, and another is spatial approximation. It's like we are describing the space. And next is apply initial and boundary condition. So I will keep this for this on hold, and we will look at these two first. Okay. So let's take an example of a string. Let's say this is a string, and let us provide some node. You can write the answer in the chat. Okay. For example, A, B, C, D. You can write it like that. Spatial approximation, correct. So the answer is spatial approximation, but I'm giving the feeling like why spatial approximation is needed. Now, if you wanted to approximate its behavior, so it can at next time it can change its shape. Okay, so it can be like this. So these nodes will now be somewhat like this. Okay, and similarly, if we take one more time step, so at every time step, the shape is getting changed. So whole shape is getting changed. Okay. But if you take only one node, it is moving from here to here. Uh, it is moving to some point. All right. So if we just describe the time, so it will be like we are going from one line to another line. But if you will describe the shape or space, then we are first describing the points, and then we are commenting on those location where those points are, how it's movable with respect to other points. So we can comment on that. Okay, so hence spatial approximation is done first, and after that, what happens that PDEs or partial differential equation converts into ODEs, ordinary differential equation. Okay, so we will write partial differential equation. What does it in space and time? It converts into ordinary differential equation in just time, because we have described the space. Now we can solve this ordinary differential equation in time using some scheme, just as RK4 method, Runge-Kutta method, or by Euler method, which was taught in the course. Okay, and finally we get the solution. So this is a general process. The first step is spatial approximation or spatial discretization. Okay. Now next is which of the following statement is true regarding time dependent problem. First is they must be linear in both time as well as primary variable. Next is they do not require boundary condition to be solved. Third is they require initial condition as well as boundary condition knowledge. Fourth is they cannot be ordinary differential equation. So the last one is cancelled because um, just mentioned before they are converted into ordinary differential equation. Then they must be linear. No, they can be non-linear also. Just like pendulum, the equation of pendulum is is this, okay, and this sine t equation of pendulum. So it's a second order equation, and you will see that sine t is not a linear. Okay, now they do not require the boundary condition to be solved. No, it requires, and actually it requires boundary condition as well as initial condition because it's a time dependent problem. So it should start with something. All right. So for example, in any vibration problem, you will see that initial conditions are provided, like where the system started and how it is evolving in time, that we have to find. But how the system started always in the thing. But there is a slight problem with this statement that sometimes initial condition is not required. That are the condition where periodic events happen, such as let's say let's say some periodic event just as our flapping wings. So if bird is flapping its wing, and so after some, let me draw a wing. Okay, so let's say this is a dragonfly wing, and after some point it will again come to the same position. Okay, let's say this is the mean position where it comes, and again it will go to next position. So at this condition, what we do is we say that initial condition is equal to final condition. So here what happens, there is no need of initial condition. The initial condition is equal to final condition. So this is where for the periodic events only. All right. So in that way, this statement is a little bit questionable, but it's okay. For now, we can take that it is a true. Yes. C. Next is consider delta t is the difference of time step. What is the order of accuracy of the Euler method in the alpha family of approximation for parabolic time dependent problem? So you all have uh, done alpha family of approximation. If not, then I will just write the equation for you. Let's say we are solving. So I said that everything converts into a ordinary differential equation. So let's say we have a ordinary differential equation as this, where u is dependent on time t, and initial condition is given that u of 0 is equal to u naught, and t is from 0 to capital T. Now this equation can be approximated by call something alpha family of approximation, where this statement can be written as 1 minus alpha us dot us is our approximated u, us plus 1 is equal to us plus 1 minus us by delta t s plus 1 for alpha from 0 to 1. Here you can see if we open the bracket, And what happens that, and let's say that s plus 1 and s are same. Let's say for this condition s is equal to uh, so there is no iteration kind of thing. Now what happened that this is us dot minus alpha us dot plus alpha us. We are taking s plus 1 is equal to s is equal to us plus 1 minus us by delta t s plus 1. Okay, in just LHS. So this will cancel this, and you what you will end in is called Euler equation, Euler method, where it's just derivative, like it's just slope. If you wanted to find slope of 2 point, so this is the equation. Okay, so hence it's just delta t, and this is the formula of alpha family of approximation. Same thing is done for double derivative, and u, one more statement is there, us plus 1 is equal to us plus delta t u dot s plus alpha. So this is the full equation, these two boxed equations. Oh, okay. Now again, in parabolic time dependent problem, temporal approximation uses the answer is straightforward, alpha family of approximation. Now the finally we have the for boundary condition u of 0 is equal to 0 and u dash of 1 is equal to 0. Two conditions are given. Now we have to check that phi naught is either 0 or 1. But we know that phi naught at 0 should be equal to 0. Okay. So the options are these two. Now phi 1 we have to find its derivative. It's x squared, for option A is x squared minus 2x, and its derivative is x squared for 2x minus 2, and at 1 its value is 0. That's what we require. So this is true. We can also check for next condition. So phi 2 is equal to x cube minus 3x. Phi 2 dash is 3x squared minus 3x, and that also becomes 0 at 1. But if we take other one, like phi 2 is equal to x power 4 minus 3x square. Now if you are finding the derivative, then 4x3 minus 6x, and if we put the value 1, then it is 4 minus 6 minus 2. This is false then. Okay, so this complete our all the tutorials, and if you have any doubt you can, okay, after these you can revise how to find global stiffness matrix of spring loaded second element system with 3 node. Okay, okay, I will come to that. So we had already done one question like this. You are saying that spring loaded two element system. I have actually a three element system. Okay, okay. So you're asking about this, where three nodes are fixed to one end. Like, okay, before that, let me answer how exactly the theory learned in this course is useful in industry. We'll come back to this first. We'll go sequentially. So industry, it runs on software. Okay, and there are high-end software just like ANSYS or other structural dynamics, or where the deformation of structures can be seen. So those are very costly as per if individual is seen. So hence, first of all, is everything comes back to the coding. Okay, but what to code? So we should have some basic principle of what should be done when we have to do some structural testing. For example, if we are making a some bridge or some structural thing, okay, and we wanted to test it out, like where it will break, how it will break. So what we'll do, first way is to build that thing and try to test it, but that is not possible for all the things. For example, if you are taking bridge, so you cannot make a bridge and then say that let it deform by something and then we will try to improve upon it. No, so we have to do some physical simulations with that. Hence, there these high-end softwares are required. But there is always research in this area, like how to find different methods by which we can find the deformation. So these courses help up in that sense that if for the basic level, if you wanted to start with something, then how to um, start building upon the blocks. So this is just a basic course of understanding between the physical and the computational aspects. That's why this course is helpful, but it's a still stage one, okay, and we have a lot of stages to cover, and it depends on the requirement actually. Ki what happens, for example, if somebody wanted to just find out the natural frequency of any body, okay, so they will be only interested in time dependent problem, which was taught in the last part, and they will just go apply FEM in a vibration body and try to approximate its natural frequency. And for example, if some excitation is into that frequency, we have to just try to avoid that. Okay, so it depends on what requirement it is. If somebody is asking for very high tech FSI study in which fluid structure interaction is going on, then we need different. I said this is one stage. Another stage will come from the fluid dynamics, and we will also look at how these two are interacting with each other. So that is a different kind of study, but still, it depends on the requirement. Okay, so this will be helpful in industry by because you can visualize now that any physical thing can be converted into computer. Like you can give computer the work of what you think that physical thing should be. Right? I hope you are getting what I am saying. Uh, okay, okay. Uh, Now coming back to okay. Um, so Bigya, so do you want this question or you wanted to see how the global stiffness matrix is? Any basic system is fine. Okay, okay. Just for revision. So let us take some first a much easier problem. So this is the problem where there are three springs and the red is denoted by global, okay, and black is for local. So what I am doing is I am taking individually these spring. So there are two methods of going. First method is to look at the nodes. So at that red points are nodes. So first method is to look at the nodes, what is happening. Okay, so that is very tough process, and we can get the solution from that. But at every node, you have to look at the direction from where it's coming, and then how we have to tackle that. So just like you can see that U1 and U2 here are having a lot of issues. If something goes wrong, there will be problem. So it's not a organized way of doing. But another way is you take it as Spring as a element. Okay, so this is the first method. Now second method is element wise. So you take elements, and then for one element you define everything. All right. So in this case, for one element, I have defined that forces are this, displacement are this, and stiffness is like this. Okay. Now, if we have taken this for one element, now we will move on to define the next same element. And if there is a repetition of behavior, so we can put in an organized way. And for example, in this, all three springs are having similar kind of uh, forcing. Okay, so these three, so it's a similar kind of, like it's a spring, and it is having at two end it is having forces. And so here, as you can see, we are just put it in a very nice organized manner. And finally, what we will do, we will look at we will find the global forces, and whatever boundary conditions we know, and we can fit that. And finally, we can solve it using finding the inverse of the matrix. Okay, so the process become very easier as uh, in case of node wise. So this is a very easy problem. I have shared these documents already. So this is tutorial number 6. So tutorial number 5. You can go to the YouTube channel also. There I have mentioned everything. Any specific thing you wanted to ask in this, like how this is the global matrix is formed. For that, just we have to look that what was the like. First of all, what we are doing, we are localizing everything. So, for example, we are just seeing at this stiffness. Okay, what is happening apart from this, we are not we don't bother, but just in this stiffness what is happening, we look at that. Then we move on to another stiffness, then another stiffness. So we are kind of making a local coordinates. Okay, now once we have made all the local description, now we will come to global description. So when we are coming to the global description, we should have this idea of what the local was. Okay, local description was. So hence it is easier to put things around. For example, in my iPad, I can just copy paste it. So I can just take this expression and put it like this. Okay, this comes here, and similarly this thing comes here, and similarly this thing comes here, because I know that these two are same, these two are same. All right. So this is called compatibility equation when we are coming from local to global. So this is for the very large system. We can so a very small system, but we can actually take this example now. And now you can just change the spring with some physical quantity, just as bar, axial bar, or if you're taking bending, then this 2 by 2 become 4 by 4. So here also you will see that all these three spring, 2 point was common. So all the 2 point, so here they are summation of the stiffnesses. Okay. So this is second point. First, second, third, fourth. So by this way, you can find uh, the global matrices. Okay, cool. Any other doubt? If not, then all the best. Uh, I will be ending the session, or I will just give you my phone number. You can WhatsApp me if you have any doubt. Okay, guys, I am ending the meet. Thank you.